Okay, hey folks, just a short video here talking about this whole idea of heating curves. We could also call them cooling curves depending on which direction we're going. So this should be pretty short and kind of gets into this idea of the stability of our phases and what we expect to happen to our phases as we either, apply heat or take heat away. So I said heating curves right there, but I'm also going to say or cooling. Okay. So here is a more traditional look at our phase diagram, right? Where in this region indicated by the solid, so at pressures and temperatures within this region, the solid will have the lowest chemical potential. So that's the phase that exists. That's the most stable phase. In this region of pressure and temperature, in this boundary, the liquid will have the lowest chemical potential, so it is the most stable. And then last, in this region of pressure and temperature, the gas phase or the vapor phase is the most stable because it has the lowest chemical potential. So what would be observed if we started like arbitrarily at some point here and cooled our sample down? Well, that would give us a cooling curve. And, I know the learning goal says heating, but we can imagine if I went the other way, it would truly be a heating curve. So this indicates time right here. But what we could also say is or Q, because what's really going on in that time is that heat is being removed. So as we allow heat to be removed, let's suppose at some steady rate, my liquid will drop in temperature until it, of course, hits the freezing point, which would be this point right there on the graph, T freeze. Okay. So now you'll notice, though, that in time here, the temperature is not changing, right? The way we would view that with added heat or removed heat, we would continually be removing heat. However, there would be no temperature change. And that's because this quantity right here corresponds to our latent heat. In that case, that would be delta H fusion, or in other places, we've called that delta H of melting, right? Same idea. So that's the penalty we have to pay, or the tax refund we're given, depending on if it's an exothermic or endothermic phase transition. So eventually, once we've paid that penalty, or that penalty has been paid out to us, the phase transition can finally happen, and now we're at the solid phase, and it continues to cool, all right? So now I don't know why that random thing is there. I just noticed that. Don't worry about that random little thing, weird. Okay, anyways. So I want to talk about thermo versus kinetics, okay? So suppose that we were able to do this in a really rapid way. So we were able to rapidly cool this thing. In this case, we might actually observe supercooling. Okay? So in other words, we might see the temperature drop so rapidly that we in fact go below the freezing point indicated right there. And eventually, oh my God, I don't know why it did that. Oh, thank God for Control Z. So eventually it would spike back up, and then we would continue along in our normal trajectory, right? So that would be my liquid cooling. And if we were able to do this in this super rapid way, we might be able to observe supercooling, where in fact our liquid gets colder than what is allowed by thermodynamics. This is a very rare and condition-specific thing. And it's also not necessarily related to how rapidly we cool this, but it can also be related to if there are seed crystals present within our liquid, that can help induce the formation of the solid more rapidly. So this idea of supercooling, or in the case of going the opposite way, superheating, is something that can be observed but it is a very kind of rare and random thing. It's a circumstantial thing that happens. All of the same, we would eventually return to our normal cooling curve where now my solid continues to cool. And if you took Gen Chem here, you might have actually observed this during the freezing point lab, which is pretty cool. Okay, so another idea behind this whole thermo versus kinetics thing, if we look at the chemical potential of graphite at room temperature, so remember that 0 means room temp. Well, as it turns out, the chemical potential of graphite at room temperature is actually lower than the chemical potential of diamond at room temperature. So what that means is actually, in fact, if you have a diamond at room temperature, it should spontaneously be converting into graphite. So if you've got a diamond ring, or if you know someone that does, you'll probably recognize that they've never once observed their diamond to spontaneously transition into a piece of graphite. And that's, again, related to the kinetics. That process is happening, but it is in fact so slow, we would never observe it in our lifetimes at room temperature, right? We can make it happen faster at elevated temperatures, or certainly at different pressures. But it is important to note that sometimes kinetics can beat out thermodynamics, but not very often. It is usually a very condition-specific type of thing. Okay, so that's all I wanted to say about heating and cooling curves and the stability of thermodynamic phases. I'll see you in the next video.